In the previous video, we discussed episodic problems. In many problems, however, the agent-environment interaction continues without end. Today, we will see how such problems can be formulated as continuing tasks. In this video, you will learn to differentiate between episodic and continuing tasks, formulate returns for continuing tasks using discounting, and describe how returns of successive time steps are related to each other. Let's look at the differences between episodic and continuing tasks. As we discussed earlier, episodic tasks break up into episodes. Every episode in an episodic task must end in a terminal state. The next episode begins independently of how the last episode ended. The return at time step t is the sum of rewards until termination. In contrast, continuing tasks cannot be broken up into independent episodes. The interaction goes on continually. There are no terminal states. To make this more concrete, consider a smart thermostat, which regulates the temperature of a building. This can be formulated as a continuing task, since the thermostat never stops interacting with the environment. The state could be the current temperature, along with details of the situation, like the time of day and the number of people in the building. There are just two actions: turn on the heater or turn it off. The reward would be -1 every time someone has to manually adjust the temperature, and 0 otherwise. To avoid negative reward, the thermostat would learn to anticipate the user's preferences. So how can we formulate the return for continuing tasks? We can try to sum up all the future rewards as we did for episodic tasks. But now we're summing over an infinite sequence. This return might not be finite. So how can we modify this sum so that it's always finite? One solution is to discount future rewards by a factor gamma called the discount rate. Gamma is at least 0 but less than 1. The return formulation can then be modified to include discounting. The effect of discounting on the return is simple. Immediate rewards contribute more to the sum. Rewards far into the future contribute less because they are multiplied by gamma raised to successively larger powers of k. Intuitively, this choice makes sense. $1 today is worth more to you than $1 in a year. We can concisely write this sum as this expression, which is guaranteed to be finite. Let's see why. Assume Rmax is the maximum reward our agent can receive at any time step. We can now upper bound the return gt by replacing every reward with Rmax. Since Rmax is just a constant, we can pull it out of the summation. Note that the second factor is just a geometric series, and the geometric series evaluates to 1 divided by 1 minus gamma. Rmax times 1 divided by 1 minus gamma is finite and is an upper bound on gt. So, we know gt is finite. Now let's look at the effect of the discount factor on the behavior of the agent. We can look at the two extreme cases, when gamma equals 0 and when gamma approaches 1. When gamma equals 0, the return is just the reward at the next time step. So the agent is short-sighted and only cares about immediate expected reward. On the other hand, when gamma approaches 1, the immediate and future rewards are weighted nearly equally in the return. The agent in this case is more far-sighted. Finally, let's discuss a simple but important property of the return. It can be written recursively. Let's factor out gamma, starting from the second term in our sum. Amazingly, the sequence in parentheses is the return on the next time step. So we can just replace it with gt plus 1. Now we have a recursive equation with gt on the left and gt plus 1 on the right. This simple equation is more powerful than it seems. In future videos, we'll exploit this equation to design learning algorithms. To recap, we learned about continuing tasks, where the agent-environment interaction goes on indefinitely. Discounting is used to ensure returns are finite, and we saw that returns can be defined recursively. See you next time.